Alright guys, this is Algebra 2 3.2.1 and we're going to be talking about rational function sticks. So we've investigated these a little bit in the past, but we're going to kind of take a look at them in a different context because we've only looked at really just the kind of parent function for a rational. We're going to be starting to look at more different types of rationals that are a little bit more complex than what we've seen before. So to start off, we're actually going to be looking at pairs of linear functions and then how those can be combined either with addition, subtraction, multiplication, or division. And saying, well, what do we get when we do that? So I would normally have you in your team go ahead and pick one of these and work on that, but I'm going to go ahead and just do one of those with us here together. So let me go ahead and open up this, change our scene to that. There we go. All right. So with that, we're going to take a look at, let's do x plus 3, and we're going to do 5x minus 9. So those are the two linear functions we're going to be working with. So first of all, I'll see, well, what happens if I add them? So if I have x plus 3 plus 5x minus 9. So I do get a more steep line because I'm kind of adding these slopes in a sense. I'm adding a slope of 1 and a slope of 5 to get a slope of 6 eventually if I were to combine these like terms, so it is more steep. But the important thing that I'm looking for here is I get another linear function, right? It's a line plus a line is going to give me a line. Now if I change the order that I add these, it's going to be the exact same thing. So the order that we add doesn't matter because again we're just combining those like terms. Now what if I change this to being subtraction, right? So if I get rid of this, make it a minus. So I still get a line here, right? But now the question is, well, if I change the order, does that affect the align? Well, it should, right? Because again, for the most part, when we add, or sorry, when we subtract, the order does matter there. And lo and behold, I get two different graphs, right? So my green graph and my purple graph are different, and that's just me ordering how I subtract them differently. So order does matter when we subtract, right? So, but the important thing, once again, is they both gave me linear. So line plus a line gave me a line minus a line gave me a line. And that's always going to be the case. Now, what if I change this and take a look at when I multiply them? So if I do these, and then I say, as opposed to subtracting, I'm going to be multiplying them. I no longer get a line, right? And this should be fairly obvious. You should have been able to predict this because you've been doing this for quite some time. If I have a binomial times a binomial, you multiply those out with either the box method or FOIL, and you get a quadratic. So you get a parabola graph out of it, right? So not a big deal there. We get a parabola. That is the first time we've seen a difference, right? It was line plus line gave us line minus line gave us line. Now it's line times line gives us a quadratic. Right? The order that I do this, again, isn't going to matter, and again, you've done that enough in the past, I'm not going to show it here, but there we go. And then the last thing that we want to take a look at is what happens if we divide these. So if I change this to division and then put my 5x minus 9 on the bottom, right next to it, I get this, which is one of those rational functions we've seen in the past, right? So we have that vertical asymptote, we have a horizontal asymptote here, and there we go. So then the question is, well, where is that vertical asymptote at? Now we talked about this in the past. What causes those vertical asymptotes is whatever value of x makes the bottom of my equation 0. So I can literally just algebraically set that 5x minus 9 equal to 0 and then solve. So I get 5x is equal to 9 divided by 5, and I get 9/5. So 9/5 is going to be the value of x that makes this 0. So I should have my vertical asymptote at 9/5. So let's check that out. X equals 9/5. And there is my asymptote right where it should be. Awesome. So our horizontal asymptote is different, right? It's shifted up a little bit from what we're used to it being. We're going to eventually go over how we can find that exactly, so don't worry about it quite yet. All I really care about you finding right now is going to be those vertical asymptotes. So don't stress out about those horizontal ones right now. All right, let's hop back over here and then take a look at this. So this is the idea of a closed set. So you've dealt with sets quite a bit in the past. You just really haven't called them sets. A set is just a term for any kind of grouping of numbers. So integers, which is a term you've heard about, is a set. It's the set of all the numbers that are whole numbers that are both positive and negative or zero. Right? So negative, so 1, 2, 3, 4, 5, all of those. -1, -2, -3, -4, -5, all of those, and then also 0, but no fractions and decimals, no things like that. That's what an integer is. We also have whole numbers. So whole numbers are just 0, 1, 2, 3, 4, 5, so no negatives. So it's like the integers, but without the negatives. It's just your kind of counting numbers, right? Stuff like that. So what a closed set means is if I do an operation with two numbers in that set, my result is also in that set. Now that seems kind of weird, like what's he talking about? Let's go over one example, right? Let's do addition with whole numbers. So any whole numbers, so 0, 1, 2, 3, 4, 5, all your counting numbers, right? If I take two of those and I add them, the result's always another whole number, right? So like 2 plus 4 is 6. That's another whole number. 10 plus 22 is 32. That's another whole number. So it doesn't matter what two whole numbers I pick. If I add them, I always get another whole number. So by definition then, whole numbers are a closed set under addition, right? How about subtraction? Well, if I take 8 minus 2, I get 6. That's another whole number. Awesome. So are they closed there? Well, no, because there's at least one counter example where I can subtract two whole numbers and not get another whole number. So what if I did 5 minus 10, right? That gives me a -5. -5 is not a whole number, it's an integer, right? So that would make it not a closed set. So we call that an open set, obviously, right? So then we can look at multiplication. Are whole numbers closed under multiplication? Take a second, think about it, and is that true? And yeah, it's true, right? And then how about division? Are whole numbers closed under division? Well, no, right? If I do 2 divided by 3, I get 2/3, which is again not a whole number, so it's not going to be closed under division, right? So we can do the same thing with integers. Integers remain closed under addition. They also remain closed under subtraction. They're closed under multiplication, but then once again, they're not closed under division. So that's it for integers. And then the last one here we're going to be talking about, what about for polynomials, right? So for polynomials, that's anything with x to the third plus x to the second plus x plus 7, whatever, right? All of those kind of quadratics or binomials, things like that we have seen in the past, right? If I add those, I'm just combining my like terms, so I just end up getting another polynomial. If I subtract them, I'm just combining like terms after I distribute that negative through, so I get another polynomial. So they're going to be closed under addition and subtraction. If I multiply them, just like we kind of saw earlier when we did the binomial times a binomial, I'll get a higher degree polynomial. So I went from linear times linear to being a quadratic, but a quadratic is still a polynomial, so it's going to stay closed there. And again, the problem is division, right? If I take a polynomial divided by a polynomial, I no longer have a polynomial because now I have a rational function. So that's the kind of big key there. So it's just like integers in that it's closed and open in those same regions. All right. So with that, let's try and take a look at this. Right. So here's an example of two polynomials. So we got p and q here. So go ahead and make a prediction as to what kind of graph you would get if we were to add them, subtract them, multiply them, and divide them. So don't try and say, well, the graph would cross here and look at this like, hey, it's this type of graph. Hey, it's a linear graph. Hey, it's a quadratic, that kind of thing. So tell me what kind of graph you would get when you add those, subtract those, multiply those, or divide those. All right. So now that you've done that, let's go ahead and check these out. So I'm going to pull up Desmos again. I will clear out all of this junk. And we're going to start by graphing, here's x to the third minus 3x minus 1. Then we want to add that to x minus 1. So this is a cubic plus a linear. We end up getting a cubic function here. So this is Still cubic, it has a bit more of a bend than we're used to with the kind of just parent function of a cubic, but it is still a cubic function, right? And that should make sense because if I add these, I'm really just combining my like terms. So my largest power of x is still going to be my x to the third, right? Then likewise, if I go to subtract these, I'm still going to get a cubic, just a different cubic, because again, I'm just combining those like terms after I distribute that negative, and I'm still going to have x to the third as my largest power. Now, what happens though if I multiply these, right? So if I multiply them, my largest power is going to end up being x to the fourth, so I should see a x to the fourth graph, which is what I see, right? X to the fourth gives us give us these kind of W shapes, and there we go, right? So there's my polynomial times, sorry, my polynomial times my binomial. I got my fourth degree there. And then what happens if I divide them? So if I do that same thing, and then I want to divide it, oops, I think Fred doesn't like that, divided by x minus 1. And in this one, we get a rational function. Now this looks a lot different than any of the other rational functions we have seen, but we should still know a few things about this, right? We should still know where that x-intercept's where the vertical asymptote is at, right? It's going to be at 1, because that's the value which makes the bottom of my fraction 0. So if I graph x equals 1, I'm still seeing that vertical asymptote where it should be, right? The difference is this is a more complex graph because this top is more complex than we've seen in the past. And I want to throw you one little hint here to kind of help you see what's going on. X to the third, if I divide x to the third by x, right, I would get x to the second. X to the second is a parabola. A parabola would have a shape that kind of looks like this, goes down and then back up. So what you're seeing is a parabola graph, but it has this asymptote right through the middle of it. And it's that asymptote which is causing our parabola to not be able to go where it wants to go, and instead it has to go towards it, then go, oops, I have to go and follow this asymptote, and it goes up early. Then on this side, it's going down towards it, and it says, oops, I can't cross the asymptote. I gotta start heading down and just follow it down as far as I can go. So that's a little bit more of an advanced thing, which we're going to focus on more in the future. But if you can kind of see that now, it's a good kind of lead-in for that stuff when we get there. All right, so with that, that is all we got for 321. Here is our homework, 63 through 69, and I will talk to you guys next time.